So in this video, we are going to be talking about point load that are slant up to a particular degree. So that's what we are going to be talking about in this video. So now, when we see point loads like this, how do we solve them? So that's what our previous videos have been talking about UDL, VDL, and point loads which are normal point loads. But in this particular case, we are going to try to find for vertical components of the loads in order to be able to start solving them. Now, as I said in my previous simply supported problems, I have always said that the first thing to do is to find for your reaction. And now finding for the reaction here, R of B times the total length, which is 1 times everything times 6 is equals to the bending moment. That is the bending moment. That is the reaction times the total length is equals to the bending moment. So now, what is the bending moment? We cannot calculate the bending moment without first getting the component of each forces in here. So now, how do we get the component of each force? That is the main problem we have now. So let's say we have a load slant here to a fixed surface at angle theta. If we go back to force and coefficient of friction, under friction and coefficient of friction, there are usually time wey they will say you drag a box on a plain floor, whereby the person that is dragging it is taking it at a rope that is 30 degree to the horizontal. 30 degree to the horizontal kinikan. Then we have a force under friction, that is under frictional force. If you can relate, when we are trying to find for, they will tell us to find for the force that is pushing it in this direction. Right here, this is the um, horizontal component. This is the horizontal component f of x. But in this place, where we are doing shearing force and bending moment, what we need here is the horizontal component, that is the force that is pushing this from on top, the force that will push it from on top, and that force that is going to determine how it will bend. So what we need to find is the force that is pushing it from the on top, that is the vertical component f of y. So now, if you are to find for the force of the vertical component, let's imagine this. Let's imagine this here as a triangle. This here, then we have our horizontal component triangle here. If we were to find for sine theta is equals to opposite over hypotenuse, that is opposite over hypotenuse. So right here, we see this as our opposite, and this is our hypotenuse right here. But you see, the force here is parallel to the force here. That means it is like the same thing. So the force here is the same thing with this. So we can use this force of x. This opposite is the the vertical component fy divided by the hypotenuse, which is there. That is the force that is usually given, which is the force F divided by force F. So now what we need here is the vertical component, which is f of x. So if we do cross multiply, we have our f of x is equal to f times sine theta. So to get our horizontal component, our vertical component is equal to f sine theta. And if we ever need to get the horizontal component, which we use to get like cross diagram or other parts, we are going to find for the horizontal component, and the horizontal component is f of y equals to f cos theta. Our f of y is equals to f cos theta. But we are not going to need it in shearing force and bending moment diagram unless we were asked to draw the thrust diagram, that is the horizontal component diagram. So but in this, we are only needing f of x, which is the horizontal component. So now, to get the horizontal component of every single one of these forces, first of all, let's start from anywhere. We can start from this one here. We have it as the force is 1.5 and this is angle 30. So therefore, the vertical component here, let's say the force at, no, since this is a load, which is W. So W of W of y, that is the vertical component, is equals to the load here, the slant load, which is 1.5 times the sin 30, so we have sin 30, and sin 30 we know is equals to 0.5, that is 1/2 using trig. So this is equals to 1.5 times 0.5, which is equals to 0.75. That is for this. Therefore the vertical component of this is 0.75. So therefore, then for this one here, we have our Wy to be equals to 0.5 sine 45. And sine 45 is equals to 0.707 if you put it in your calculator. So that is equals to 0.5 times 0.707, which will eventually give us 0.353. So therefore, the vertical component of this is 0.353. And also for the third one, which is Wy, that is equals to 1 times sine 45, that is equals to 1 times 0.707, which will still give us 0.707. So therefore this here is 0.707. So here we have gotten our vertical forces, then we can go directly and start finding for our reactions at A and B. So now our reaction at B, RB times 6 is equals to, we have 0.707 times the distance, which is 1, 0.707 times 1, then plus this here, which is 0.353 times 2.5, that is 1.5 plus 1, then plus 0.75 times 5, which is the bending moment. So everything divided by 6, when we calculate everything, we are going to get our reaction at B to be equals to 0.765 kilonewtons. So our RB is equals to 0.765 kilonewton. That's our RB. And now to our reaction at A, we know that RA plus RB is equal to the total amount of shearing force. The total amount of shearing force is 0.707 plus 0.353 plus 0.75. So therefore we have our RA to be equal to all this, which is 0.707 plus 0.353 plus 0.75 minus the RB, which is equals to 0.765. We will get our RA to be equals to 1.045. So our bending moment, our reaction moment at A, our reacting force at A will be equals to 1.045 kilonewton. 1.045 kilonewton. So that will be that. Then we move on to our shearing forces. We have our shearing force at B is equals to the force there, which is RB. We have 0.765, and our shearing force at C is equals to 0.765 minus 0.75, which is equals to 0.015. 0.015. Then we have our shearing force at D to be equals to 0.765 minus 0.75, then minus 0.353, which would be equals to minus 0.338 minus 0.338 kilonewton. Let's not forget our kilonewton here. We also have our shearing force at E is equals to minus 7 minus 0.765 minus 0.75 minus 0.353 minus 0.707, which will give us our shearing force at E is going to give us minus 1.045, and our shearing force at A would also be equals to minus 1.045. So that will be it for our shearing forces. Then we move on to our bending moment. Our bending moment right here at B is equals to 0 because there is no force times this and there is no distance there. We have our bending moments. Our bending moments at C to be equals to the reacting force times the distance, which is 0.765 times distance 2 meter, which will eventually give us 1.53 kilonewton meter. So if we move on to our bending moment at D, our bending moment at D is 0.765 times, we have 2 and 1.5 times 3.5 times 3.5, then minus this one right here, which is 0.75 minus 1 times 1.5 times 1.5, then that is for that. So it will give us 1.55 kilonewton meter. Then also if we move to our bending moment at E, our bending moment at E would be equals to 0.765 minus 0.765 times the distance here, which will be times 5. 0.765 times 5 minus 0.75 times this one here and this one, which is times 3. Then we have minus 0.353 times 1.5, 0.353 times 1.5. So if we do everything together, we are going to get 1.045 kilonewton meter. And then our bending moment at the edge is 0. So we have our bending moment at A will be equal to 0 kilonewton meter. So that will be our bending moment and our shearing forces calculation right here. So now moving to the diagram, which is the purpose of the calculation, we put our broken line, we trace it down, trace it down. So now to our shearing force diagram, we draw a neutral line right here. Shearing force at B is 0.765. We take it up straight line. Our shearing force at C is 0.015. Take it down straight line. We have 0.765, 0.015. Then we also have shearing force at D minus 0.0338. We take it down 0.338, 338, and we also take it down to minus 1.045. So we take it down 1.045. That is from E to A. So this is negative and this is positive. That is for that. Then our bending moment diagram, we do our neutral line right here. Bending moment at B 0, bending moment at C 1.53. We take it up to 1.53. Then our bending moment at D would be equals to 1.55. We have 1.55. Our bending moment at E is 1.045. So that will be lower than 1.53. We have this at 1.045. And our bending moment here is expected to be 0. So this is our bending moment diagram. This is positive here. Our bending moment diagram and our shearing force diagram. Our bending moment diagram and our shearing force diagram for loads that are tilted at a particular angle.